an additional step is taken towards the realization of the long-promised concept of extremely rapid computing. All that is required is one of the materials that is the hardest in the world. Here we will talk about diamond idea for quantum computer. If you are new, then subscribe to Sparrow now for more updates. The field of quantum mechanics has evolved significantly over the years. A few decades ago, everyone was talking about how, at the very small scales of atoms, energy comes in chunks or quanta. These chunks are not continuous, like water, but discrete, like money. This was the topic that dominated the conversation. Even light has a grainy texture because it is composed of tiny packets of energy known as photons. However, forget about all of that. Quantum physicists don't really talk about quanta anymore. Instead, they talk about information. They have a hunch that quantum mechanics is, at its core, a theory about the kinds of information that can and cannot be obtained about the world. Examples of this idea include the well-known uncertainty principle, as well as the concept that quantum objects can exist in either this location or that location. However, there's more to it than just theory. The new perspective has the potential to be applied in the form of something that is referred to as quantum information technology. This refers to methods of storing, transmitting, and manipulating information that function according to the rules of quantum mechanics as opposed to the classical rules that govern our everyday world. The most well-known application of this technology is the quantum computer, which could use quantum principles to achieve power levels that are significantly higher than those of the devices on which you and I are currently working. Even though experts in the field are aware of how quantum computers ought to operate, no one is aware of how to actually construct one. Scientists have created toy quantum computers with only a handful of bits, in comparison to the billions of bits in your smartphone, and some companies are even starting to offer primitive versions for sale, despite the skepticism of some industry professionals. However, despite encouraging reports of minor advances made over the course of the past few years, there is still no possibility that you will have access to a quantum laptop that is of any use in the not-too-distant future. On the other hand, researchers in Germany have just published a finding that could represent a significant advancement. Diamond has been suggested as the prime candidate for use in the construction of quantum computers. Don't lose hope. This does not necessarily mean that they will cost an arm and a leg. The extremely thin diamond films that are required for such devices do not have to be mined. Rather, they can be synthesized artificially from carbon-rich gases such as methane. This eliminates the need for mining. It's not exactly cheap, but then again, neither are the methods required to make semiconductor films for a whole host of electronic devices that already exist. The process of encoding and manipulating information in binary form, also known as bits, which are represented as either zeros or ones, is fundamental to the operation of both traditional and quantum computers. Individual nitrogen atoms that have been implanted into a diamond film, as proposed by Florian Dold of the University of Stuttgart and his fellow researchers at the institution, are thought to be the ideal elements for storing this information on a quantum computer. Because of a quantum property known as spin, nitrogen atoms have an extra electron compared to the carbon atoms in diamonds. This extra electron has the potential to exist in two distinct quantum states. An electron spin can be thought of as pointing either up or down, similar to how the poles of a magnet, which are used to store information in magnetic disks and tapes, can be considered to point in either direction. Before we move any further, subscribe to Sparrow now. This much has been known for some time, and others have performed quantum computing experiments using nitrogen-doped diamond. The breakthrough that was made by Dold and his colleagues was to demonstrate how they could place these spins in nitrogen electrons without having to bring the temperature of the diamond down to extremely low levels first. Within a whirl. Because a collection of quantum bits could exist in many more different states than the same number of classical bits, quantum computers have the potential to be significantly more powerful than their classical counterparts. This is due to the fact that quantum particles can coexist in two or more distinct states at the same time, a phenomenon that is referred to as a superposition of states. Therefore, each quantum bit, also known as a qubit, can be either a 1 or a 0, or it can be a mixture of the two. As a consequence of this, a collection of qubits would be able to carry out a wide variety of computations all at once, as opposed to an ordinary computer, which would have to carry out these operations one after the other. It is generally believed that this can only be accomplished by entangling the qubits in some way. Because of this, the quantum state of one of them is dependent on the states of the others, despite the fact that these states aren't actually assigned until they are measured. This is because of the entanglement that exists between them. In other words, if you entangle two spins that are facing in opposite directions and measure one of them as being up, the other spin instantly becomes down, regardless of how far away it is. This is true even if the spins are very far apart. This entanglement is now a well-established fact, despite the fact that early quantum theorists, including Einstein, thought it would be impossible to achieve this. However, here's the catch. Just like the majority of quantum properties, entanglement appears to be quite fragile. It is possible for a pair of entangled particles to lose their special connection as a result of the jostling that is caused by the movement of other atoms, causing their states to become independent of each other. In order to maintain entanglement, the particles typically need to be cooled to temperatures very close to absolute zero in order to eliminate the jostling. However, a quantum computer that needs to be kept at such low temperatures will never find much of a market for its product. However, Dold and his colleagues have demonstrated that two nitrogen atoms that are trapped in diamond and spaced tens of nanometers apart can be kept entangled at room temperature for more than a millisecond, thousandth of a second, which could be long enough to perform quantum calculations. They fired a beam of nitrogen ions, charged atoms, at a diamond film through a mask with holes about 20 nanometers apart in order to entangle the atoms using microwave photons. The mask had holes about 20 nanometers apart in each of its holes. The argument in favor of nitrogen-doped diamond quantum computers has been bolstered further by a paper written by Martin Plenio of the University of Ulm in Germany and his co-workers. They have shown that in theory, and no more than that yet, such a system could be used as a quantum simulator, which is a type of quantum computer that can calculate how the behavior of other quantum systems will be predicted. This is a significant step forward in the development of nitrogen, due to the mathematics that is required to predict quantum behavior is difficult, and traditional computers have a difficult time keeping up with it. However, a quantum simulator, which operates according to quantum rules, already has the quantum nest built into its components, and as a result, it is able to perform such calculations with a great deal more ease. Diamond, of all the possible solutions, could smooth out the rough edges of the problem. That's it for today. Thanks for watching.